All right, let's get into it. Today, we're basically becoming geometric detectives. We're going to be cracking the code of congruent triangles. Now, this is a really cool concept that lets us prove two shapes are exact copies of each other, but, and this is the best part, without having to measure every single little thing. So let's get started.
So let me ask you a question. Imagine you're building something. Maybe you're an engineer, maybe you're putting together some furniture from a box. And you need to make sure one part is a perfect, exact copy of another. How do you know for sure that it's identical?
Well, you could measure everything, right? For triangle, that's 3 sides and 3 angles. But take a look at a complex structure like this one. Can you imagine measuring every single piece? It would be a total nightmare. It's slow, it's tedious, there has to be a better way.
And there is. And it all comes down to one really powerful word: congruence. This is the key. This is the idea that lets us prove two shapes are identical without all that extra boring work.
So what does congruent actually mean? Well, the official definition says that if you could somehow pick one triangle up and place it right on top of the other, they would match up perfectly, with no bit sticking out. You know, think of them like identical twins. Every single part is exactly the same. And this brings us to the most important point. For two triangles to be truly congruent, they have to have the same shape and the same size. It's not one or the other, it has to be both. You can see it in the markings here. Every matching angle is equal, and every matching side has the exact same length.
Okay, so this is where it gets really fun, because we don't actually need to check all 6 parts. We've got shortcuts, and we're going to call them our secret codes. These are the absolute minimum bits of information you need to prove that two triangles are perfect copies.
So our very first secret code is SSS. Super simple. And as you've probably already guessed, those letters stand for side, side, side. What this means is, if you can just show that all 3 sides of one triangle have the same length as the 3 corresponding sides of another triangle, that's it. You're done. They're congruent. The reason this works is that 3 specific side lengths can only form one possible triangle. The angles get locked into place automatically. They're perfect clones.
Awesome. Let's move on to our next code. Code number 2 is SAS. Now this stands for side angle side, but I'll give you a heads up, the order of these letters is a really big deal.
For side angle side to work, you have to know that 2 sides are equal, and the angle that's included between those 2 sides is also equal. Think of it like the angle is sandwiched by the 2 sides you know. If you've got that specific combo, you've got congruence. See the pattern here? Our third secret code is ASA. Any guesses? Yup, you got it. Angle, side, angle. And just like our last code, the order here is everything. ASA works if you know 2 angles are equal and the side that is included between them is also equal. Again, that side has to be the one that connects the 2 angles you're looking at. All right, time for our 4th code. This one is a little different but super useful. It's AAS, which, you guessed it, is angle, angle, side. So this is kind of like ASA's cousin. It tells us that if you know 2 angles and a side that is not between them are equal, the triangles are still congruent. So you might be thinking, wait, how is that different from the last one? That's a great question. Let's clear that up right now, because it's a common mix-up. With ASA, the side you're looking at is literally trapped between the 2 angles. It's stuck right there. But with AAS, you know 2 angles and then some other side that isn't connecting them. The good news is both of them work. You just need to know which situation you're dealing with. Now, for a bonus round, we have a special code, a shortcut that only works for one specific kind of triangle, the right-angled triangle.
So, meet RHS. This one's a little different. R stands for a right angle, so both triangles have to have a 90-degree angle. H stands for the hypotenuse. That's the longest side, the one opposite the right angle. And S stands for any one of the other corresponding sides. If you can check those 3 boxes, you've got congruence.
Okay, so we have our codes. We're almost there. But there's one more pro tip you absolutely need to know to really nail this. It's all about how you write down your final answer. It's not just about being right. It's about communicating it the right way. The source material actually says it perfectly here. When you write that one triangle is congruent to another, the order of the letters you use for the corners, the vertices, matters a lot. It's not random, it's like a map that tells anyone reading your work exactly which parts match up. Check this out. If you write that triangle ABC is congruent to triangle DEF, you're telling me that angle A matches angle D, B matches E, and C matches F. But look at the wrong example. If you write DFE, you're saying that B matches F and C matches E, which is just not true. See? The order isn't just a tiny detail, it is the proof.
So let's do a quick recap of your new congruence toolkit. You now have 5 amazing codes in your back pocket. You've got side, 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 angle, side, angle, angle, side, and of course our special case for right triangles, right angle, hypotenuse, side. These are your shortcuts to proving things are identical. And that's it. But really, it's just the beginning for you. Now that you have these codes, you have a totally new way of looking at the world. Seriously, look around you, at bridges, buildings, even things in nature. What hidden structures, what complex shapes can you now prove are made of identical pieces?